designs. And now we're going to move into the radial flow system, which is a design developed to get away from the problems of the dual bed VBS design. Okay? So the radial flow design is a little more sophisticated because it does have it replaces a vertical airflow, but the reality of it is the airflow inside the unit is horizontal. So this is what a radial flow system looks like. Again, it's a round tank because the guys who are looking to replace the dual bed design kept thinking round, and that's fine. It works fine for this unit. Okay, this is going to be a cross section. I'm going to draw a cross section of the unit. All right, so let me draw it first, and then I'll describe it a little bit better. Because I need to show you a top view at the same time. Okay. All right, so if we wanted to, this is the cross-sectional view of that, okay? So we're taking a look at the side view of it and the top view, and hopefully you're getting that there is a hollow cylinder. So this is the absorbent media here, all right? Media here, and this is the absorbent media inside the system here, right? So this is perf screen here, perforated screen. So it's a wall with a bunch of holes in it, and so the radial flow has a hollow cylinder of carbon on the inside. So what happens is the air comes in the inside and swirls around this outside area. This is why it's called radial flow, because the air is coming in at a tangential point right here and swirls around, okay? And then eventually, as it's swirling around, it makes it through, it percolates through the absorbent media here, all right? Hopefully evenly percolates through the absorbent media, which is illustrated here, okay? So this is the odorous air, and this is the clean air, and this inside. So the odorous air is swirling around this outside plenum area, we say. It's percolating through the carbon bed, and then it goes out through the center here.
So the blower would be on the bottom on this?
So yeah, that's correct. And so I guess we could kind of show the blower like this, yeah. Now it doesn't necessarily have to be in the bottom. It could be up actually in the middle in blowing the air around to kind of evenly flow, but it works kind of fine just to have it at the bottom to swirl that air, and that's why we call it the vortex, because it's kind of like a little tornado on the inside, right? It's swirling around, swirling around, swirling around. So you should have really even pressure in this whole outer plenum here, all right? And then the air goes through there. So now, what sets the design of the velocity through the carbon? Well, now you have to determine the area of this whole cylinder here and your total airflow, and then you can figure out your airflow based on that. We can have a spreadsheet set up to be able to do that, because it gets a little more complicated because you're dealing with cylinders and everything here. But the advantage here is that we're able to do two things to increase airflow. One is we can change the diameter, basically, of this cylinder here, right?
On the inside.
On the inside. So we can make it narrow or wider, okay, to increase the amount of carbon. But then the other is that we can increase or decrease the height of this. So what we're doing is just making this cylinder larger. So how do we make the cylinder larger? Well, we can increase the diameter of the cylinder, and we can increase the height of the cylinder as well. Okay, so this is really nice, and typically what you can do is you can make a system that is 7.5 feet in diameter here, which I forget the height on it, but it can give you at least 15,000 CFM. Okay, so now all of a sudden we're able to do more airflow in a system that's a smaller diameter with it. So why is this important? Well, one of the keys is, as you guys know, we get a lot of our fiberglass made in Asia. Well, if we can keep the diameter of this system below 7.5 feet in diameter, we can stuff it into an ocean container. Okay? That's a big deal for us to be able to do that. We have a very high quality, reliable fiberglass partner. And if you look at the dimensions of an ocean container, it's a little bit bigger than 7.5 feet. And so they can make a unit. So if we have to kind of maintain the diameter at 7.5 feet, well, what kind of length can we deal with? Well, theoretically, an ocean container is 40 feet long. So we could make this thing 40 feet tall, right? Reality is we're probably not going to make something 7.5 feet in diameter and 40 feet tall. But, you know, we could easily make it 20 feet tall if we wanted to, okay? So this is the advantage of this design, all right? So commercially, where do we sit with this system? Well, unfortunately, one of our competitors, a fiberglass guy, has gone in and he has a good design for this deal, and he can make it pretty cost effectively out of fiberglass, and he gets most of those projects. We don't sell a whole lot of radial flow systems. But on the other hand, we haven't really been really promoting this design very much, because we have other designs we prefer to see as well, okay? And we should note that the material of construction for this can actually, we don't even have to build this out of fiberglass. We can build this out of HDPE, like plastic sheet. We got a supplier here in the US that can build it out of that. And that's usually fairly low cost as well for it. So if we can get this specified by a customer that it's got to be made in HDPE, then we'll have a preference on the project as opposed to fiberglass with these other guys. So,
how do you change the media in that?
Yeah. So you change the media out because up on top there's some type of fill chute here on top here that you go in and you climb up on top and you vacuum the carbon out, the absorbent media out, and that can be a little problematic.